Hi folks, and welcome back to Physics with Captain Rod. I'm making this one out to help you out with number 26 in your Unit 1 homework. Now 26 gets its own video. I'm only going to include this one problem because this is the first one I think I've talked about here where we're going to look at a velocity graph. Very important when you're doing any sort of work with graphs, you know exactly what type of graph you're looking at. So this graph isn't telling us where an object is. It tells us how fast it's moving and in what direction. So for example, at t equals 0, we are here on the graph, 1, 2, 3, 4, 5, 6, 7, 8. That's about minus 8 meters per second. All right, if I was assuming right positive, that point is indicating that the object is moving left at 8 meters per second. All right, so just making sure everybody thoroughly understands what that's saying. All right, so this one says to find the velocity at 3 seconds. Now, in the previous problems, we were getting velocity by delta x over delta t. But that's because we were looking at graphs that were x against time, and we were using slope to do so. All right, but here we have the graph is telling us the velocity at any given time. So, for example, the particle's velocity at t equals 0. Is 8 meters per second left, or you could just say minus 8 meters per second is just fine. Repeat for 3. When it says what is the particle's velocity, go to 3 seconds on the graph and just read it. It's not a slope calculation. Now the next one here that says what is the particle's acceleration. So acceleration, when you calculate it, that's equal to change in velocity over change in time. And again, you know, when you see change in something over change in something, these are slopes. This is the slope of a velocity against time graph, which is what we are looking at here. So really, in reality, these are slope. This is a slope question, right? The acceleration at 3 seconds. So 1, 2, 3. 3 seconds on the graph is roughly here. This graph is basically linear, so what that means is you can choose any 2 points on that graph and then calculate the slope. Right, displacement questions from 0 to 3. Let me get rid of some of that stuff I just typed. All right, so displacement. So delta x, your displacement, is equal to your average velocity times time. I'm getting that right from this, basically, just slight rearrangement. And again, that's equal to area here because velocity is the vertical on this graph and the delta t is the horizontal. So from 0 to 3, right, 3 seconds is here, we're here on the graph. What we're looking for is this area right here. Now, that is a trapezoidal area. So you can either, if you're not familiar with that, you can go back to my video on how to find the area of trapezoid, and I'm not going to cover that now. Or you can just do rectangle, triangle, perfectly acceptable to say, all right, there's a rectangle, what's the area? Here's a triangle, what's the area? And that's perfectly acceptable as well. So that should get you through that one. I guess I'll scroll down and see, is there another question here? Ooh, a couple more. Total displacement for the entire graph. All right, so let me do some color coding. I'm going to do to the green here. I use green for left. In this region right here, the velocities are all negative. So this green area is going to give us some sort of displacement to the left. Now, in this region, right, these velocities are all positive, which again, if we assume right positive, those velocities are all to the right. And then this area would give the delta x in that region. Then there's no area for the rest of this here. So add the green area to the red area. That will tell you the net displacement for the entire graph. Okay, total distance traveled for the entire graph. All right, so when you're finding displacements, right, I'll put your delta, oops, I wanted to go back to standard black here. Your delta x total, I'll say is your delta x, I'll say green, plus your delta x red. And this one is going to be a negative number. This one is going to be a positive number because During the first half of the trip, the object's velocities were negative, meaning going to the left. Second half here, velocities are positive, meaning to the right. Now, distance is not a vector. We don't care about direction. So our distance here is going to be when we add the magnitude of this, because that's going to tell us the how far to the magnitude of this. So basically add the magnitude of the delta x, the green delta x, plus the magnitude of the red delta x, I'll call it, and that will give the total distance traveled. Again, see why the magnitudes? Because when you're doing distance, distance doesn't care about direction. Oh, whoops. So, and then explain why these things are different, and I basically kind of did that for you. But okay, anyway, I hope that this helps get you through this problem. Have a great day.